thinking about these interventions. Once you start formalizing them on networks, there is a very nice combinatorial interpretation. So for pharmaceutical interventions, which is like when you take vaccines or antivirals, this is like removing nodes. So if these nodes take the vaccine, they don't contribute to the disease spread, so you can remove them, and then you can look at properties of the residual graph. If the vaccine works has efficacy 1, so if it gives you complete protection, it's like deterministic deletions. But if it is it gives you protection with some probability, then it's like these nodes are removed with some probability, and so now you look at you have random subgraphs and you look at properties of those. On the other hand, if you have non-pharmaceutical interventions, so like social distancing, school closure, and so on, so this is like removing edges. So there are a huge number of issues when you start looking at these as optimization problems. So the first is resource constraints. You have budget for how many vaccines are possible. There are many objective functions like we saw earlier, and these are not these are often competing. So reducing one might make the other one worse, and so on. So one needs to do multi-criteria optimization. There are issues of implementability and compliance. So you can't for intervention to be practical, one can't say, okay, I'm going to vaccinate this guy and this guy and this guy and so on. They have to be, I know, like to be able to describe them succinctly. So people in this age group or people living here and so on. And then there are these individual versus social good issues. And finally, once you look at these problems in networks, these problems become really computationally really hard. So computing even basic properties related to epidemics is very challenging. This becomes the network reliability problem. So it's I'm not going to talk about these complexity classes, but I'm happy to discuss later if there are questions. Even simplistic versions of these optimization problems are NP hard, so one can't expect exact solutions. The goal would be to get approximation results with good guarantees, and because of if you're looking at large networks, simple brute force methods are not going to scale. There's a lot of work in OR and in public health on using meta heuristics, but they don't give any insights into how well they work. So our approach is to try to formalize these interventions in terms of the network structure. And so I'll start with the first one on looking at the social objective, minimizing the number of infections, and this is like centralized setting. So the network who are overseas, so the government or public health planners, they are trying to figure out whom to vaccinate. Okay, so we don't know how to do this in the SIR model. That's much harder. Instead, we are going to look at this other model called the SIS model. So in this model, nodes are only in 2 states, susceptible or infectious. So they're going to be infectious for some time and then become susceptible again, so they can keep getting reinfected. So this is a model of endemic diseases, so like malaria and so on. So and beta and delta are the transmission and recovery rates. Rho of so A is the adjacency matrix of this graph. So it has the ijth entry is 1 if I and j come in contact, and rho A is the largest eigenvalue of the spectral radius. So this threshold T is going to be important for us. And the other quantity which we need is what is known as the isoparametric constant. So for a given set, so this is a network for a given set, we look at this ratio of number of edges going out of the set over its the size of the set. So for this set here, this ratio is there are 2 edges going out over the size 2/6, and the isoparametric constant is look at this, the min of this ratio over all subsets of certain size. So in this example here, this min is going to be less than or equal to 1/3. So the spectral radius is a very well studied quantity. It's sandwiched between the average degree in the graph and the maximum degree in the graph. Okay, so the reason to look at the SIS model is there is a very nice characterization of the dynamics in terms of spectral properties, which one can then use to try to design interventions. So there is this very nice paper by Ganesh and others. What they show is the time to die out in the SIS model can be characterized in terms of the spectral radius and the isoparametric constant. So you should note that because of in the SIS model, since you only have S and I states, the only limiting state is all susceptible. So eventually the disease is going to die out. Right? So the only interesting quantity is how long it takes to die out. So what Ganesh et al. Show is if the first eigenvalue is below a threshold, it dies out fast, and I'm going to just show you what their result is. And on the other hand, if the isoparametric ratio is large, then it stays for a long time. And the people have extended it using various kinds of heuristic assumptions to other models, including the SEIR model, but it's not as rigorous. So formally what Ganesh et al. Show is if the spectral radius is below this threshold, then the expected time to die out is basically logarithmic in n. Yeah. So in this, so P is beta here. So the way I'm stating it is for constant uniform. You mean uniform, right? But this can be extended if you have non-uniform betas. But if they are symmetric, then the result can still hold. Then you can write it in terms of the eigenvalue of that beta matrix.
Sorry, what's the isoparametric constant again?
So the it's what is known as also as the expander. So for a given set, look at the number of edges which go out divided by size of that set. So that is the expansion for that set. And now we look at the min of this ratio over all sets, and this is a generalized one. So you look at sets up to size m. So this is overall small sets, the ratio of number of edges which go out to the size of that set. So this is an what is known as the expansion, and this is related to mixing time of random walks. So basically, if you have a random walk and if you have few edges going out, then it's going to be stuck inside.
Minimization of surface to volume.
Yes, exactly. That's what I mean. It was originally that's how it was derived, and it's the discrete analog of that. So what Ganesh et al. Show is if the expansion is, if the graph is an expander, then it actually stays for the time to die out is exponential. So there is a gap between these two, and just show, again, this is still from Ganesh's paper. What this tells us is so in the hypercube, if beta is below this value, there's fast die out. If it is more than this, it's slow die out. And in Erdős-Rényi, these two conditions are really close. It's like 1 over np, the average degree. In power law graphs, it's much more complicated, and it also depends on whether the exponent is below 2.5 or about 2.5 and so on. So in general, there's a gap between these two conditions. Okay, but empirically, when we tested it out, it looks like if the first eigenvalue is a few times larger than this threshold, then it stays for relatively longer time compared to when it is below. So what this suggests is if you assume that this condition is kind of if and only if, that if the first eigenvalue below threshold is a way of brings the infection down, and if it is sufficiently larger than the threshold, then the infection stays, then that gives you a nice way of trying to design interventions. So if basically you can try to reduce the eigenvalue below threshold, and so that can be the basis for designing an intervention. And sorry.
That this long tail with some minimum number of cases for a long time. What do you mean by last long? What is the definition?
So this is defined for the statement is for SIS. So the epidemic has not died down if there is at least one case. See, the limiting state in SIS is that there are no infections, right? It's all less. So this is basically the epidemic hasn't died out if there's at least one case, and we are looking at that. And this, in reality, it's not like a steady state. There is fluctuation number of infections before it dies out. Empirically, we also tried this on the SIR model itself. So look at just the outbreak size, and it also seems to just empirically show interesting regimes like this. If the first eigenvalue is low, then the number of outbreak size is small, and if it's large, then the outbreak size is large. But there's no, I mean, we don't know what the statement is. I should just point out that these other papers, they claim to extend this to all these other models, but what so first thing, they relax this, so they make a assumption about independence, which is actually pretty crucial, and what they instead, they don't really look at time to die out. Their statement is that if the eigenvalue is below threshold, there is only one equilibrium in some nonlinear dynamical system which describes the evolution of the probability vector. And if it is above this threshold, then there are multiple equilibria, and so from there they say that there can be a large outbreak if it's above threshold. So it's not super rigorous, but maybe that can be made rigorous. I don't know. Sure.
Like how these two parameters, rho and eta are related, because you are
right. Okay. So we don't. Right. So we don't know. So in general, there's no. They're completely different parameters. If you look at specific classes of networks, they like in random graph models and well-structured networks, there is some gap, but not a whole lot. So in GNP, for instance, they're really close. In power law networks, there is some gap, which depends on the exponent and so on. So right. So in general, there is a gap between these. We don't know. That's a big open question whether one can bring them closer or not. Okay, so for our purpose, basically, once you take this characterization as a starting point, then that gives a very nice way of formalizing interventions. So you can just try to reduce the spectral radius, and from graph theory, we know that you can reduce the eigenvalues by either removing nodes, which is like capturing vaccination, or removing edges, which is like social distancing. So this gives us this nice problem of spectral radius minimization. So given the graph and costs and the threshold, you want to remove the cheapest set of edges, so this eigenvalue goes below threshold. Similarly, you can have a node version. So this is an interesting problem in its own right, and there's been some work before, mostly heuristic. There's some interesting heuristics which were proposed, one based on like the components of the eigenvector, so rank order nodes based on eigenvector values. So from the Perron-Frobenius theorem, the first eigenvector is going to be positive. So if you use that to guide whom to vaccinate, that seems to work pretty well in practice, and there's also the natural degree based ones and so on. So I'll describe very quickly one algorithm which is based on looking at walks in the graph, and one can say something about its performance as well. So, so given this graph, we look a walk is something which starts at some node and goes around and then comes back. So here this is a walk of size 6. So it starts here 1, 2, 3, 4, 5, 6, and notice that this edge has been repeated, and that's fine. So these are closed walks. So let WKG denote the set of closed walks. We'll say an edge hits or lies on this walk if it's a part of it, and NEG is the number of walks which contain this edge. So this algorithm is really simple, and we'll call it a greedy walk. So while there are enough walks, we pick an edge which hits the most number of walks. If there are costs on the edges, then we pick an edge which maximizes this ratio, which gives the most number of walks hit per cost, and we pick that edge and remove it and repeat. Okay, so that's this algorithm. So what one can show about this algorithm is once you run it enough so that the number of walks is below some value, the first eigenvalue is close to t, and the cost of this the solution that you pick, it's more than the optimum by this factor. So this E opt is the optimum solution which brings, for in this instance, brings the eigenvalue below t. So what one can show from greedy walk is the cost of the solution is the optimum times some logarithmic factor, actually polylogarithmic factor. And this can be easily extended to a node version as well. So this algorithm is easy to implement, and I have a proof, but maybe I should skip that. And I'll just say that by some other techniques, so by primal dual algorithms, one can improve this performance from log square to log n and beyond. Okay, so it works better than all the other heuristics from before, and this is a plot of the maximum eigenvalue in the residual graph with versus edges removed, and lower is better, and the greedy walk does better than all prior ones. And I'll also say that one can construct instances where the eigenscore based method or the degree based method doesn't do well. One can give tight lower bounds. So let me move on. I can come back to these to the proofs or more details if there are any questions. But let me go on to the other parts since I want to also show you some tools that are there on our web page. So so what we've talked so far is you're given this instance, you can decide whom to vaccinate, and then you're trying to do this optimally. Clearly, there's if you try to come up with something like this, it's not going to people are not necessarily going to comply, right? So some people will, some people don't, and how do you take that into account? So one way to do that is extend this to a group level. So imagine the population is split into groups V1 through Vk. Each Vi might be like a demographic group, so kids or seniors or people living in this area and so on. And we model compliance by saying that if you allocate Ni vaccines to the set Vi, they are going to be distributed randomly within that set. You don't have any control. Once you say that, okay, I'm going to distribute 10 vaccines to this group of kids, there is no control over how that's going to get actually be deployed. Some 10 random kids in that group will do that. So that gives us this group level problem. So find a subset of sorry, I should have changed this. So the problem is actually decide how much you allocate for each group, and once you decide how much you allocate, the cost, the benefit of that is going to be evaluated in the following way. overall random subsets of this group of this size, look at the eigenvalue of the residual graph. Right, so now we have many instances of this. It's going to be, we need to look at the expected eigenvalue over all random choices of SI subsets of Vi. And the question now is the expected eigenvalue should be as small as possible. Right, so sorry, there's a typo, missing, incomplete description here. So this is the extension of this problem to a group level, which takes compliance into account. And it turns out this greedy work method can be extended to a group level. One can basically, instead of now looking at number of walks hit, we look at the expected number of walks hit when you have a certain number of vaccines allocated to each group. And this is basically a submodular function on a lattice, and one can show that it gives us similar guarantees. Okay, so again, both the problems that we looked at so far, they were from a centralized perspective. Some public health agency is trying to figure out how to allocate vaccines and taking some individual constraints into account. The next thing is how do you bring in individual level objectives? So this becomes a very classic game theoretic setting. And there's been a lot of work on vaccination games, especially in the differential equation framework. So the problem is what is an individual, the strategic decision is whether to get vaccinated or not. And if a person gets vaccinated, there's a cost of getting vaccinated. If he is not vaccinated, then there is some chance that he might get infected, and so there is the individual utility is a combination of these two. So all the work which has been done on vaccination games, it either simplifies the network, so it assumes simple mixing patterns. So one extreme of that is where you have homogeneous mixing, and so you can use differential equation methods, or you can use random graph analysis, or they simplify the disease transmission model. So for instance, they take a transmission probability of 1. So our spectral graph characterization allows us to formulate, to take both of these into account, and I'll just state the formulation and some results that we have, and go on to the last one. So let A denote the strategy profile. So X is 1 if node X is vaccinated. So now one can define the cost of a node for a given strategy profile in the following way. So if this node is vaccinated, then it incurs a vaccination cost of Z. If this node is not vaccinated and the residual subgraph has eigenvalue below T, then the assumption here is the disease is going to die out soon, so it has a low cost, which is basically low risk of infection. On the other hand, if it is not vaccinated and the eigenvalue of the residual graph is more than T, then it incurs a large cost because the disease is going to stay for long. Right? So this gives us a nice way of expressing the cost vector, the cost, which takes both the network structure and the disease model into account. And so now a Nash equilibrium in this game would be a strategy vector in which no node has incentive to deviate unilaterally, and the social optimum is a strategy vector which minimizes the sum of these costs. So again, using the spectral characterization, once we formulate it in this form, there's a lot of useful structure that one can build on. It turns out this game is a really simple one. Every minimal set turns out to be a Nash equilibrium. So any minimal set whose removal brings the eigenvalue below threshold is a Nash. Finding low cost strategies is hard. And we looked at the price of anarchy, which is the cost of the most expensive Nash to the cost of the cheapest Nash, and there's some nice bounds one can derive in random graphs. So in like the Chung-Lu network with a power law exponent, this ratio scales as this threshold raised to beta. Okay, so the other thing which needs to be taken into account is once a disease starts, people actually change their behavior. So this is what is known as coevolution. So if an epidemic is going on, people reduce their contacts. There is also risk behavior. So if they feel they are protected, they are going to increase their contacts. Sometimes it can have counterintuitive effects. So like this has been documented in the case of HIV. These vaccines are not foolproof, and they take some protective mechanisms, but they doesn't protect them as much, and it ends up causing more infections. So we have looked at the effect of such risk behavior on the epidemic size, and I'll probably skip. So let me spend a few minutes on this last one, and then I'll show you one of our simulation tools. This tries to bring all of these issues together. It's combining individual and social objectives. This is a much harder problem. So this right now is a simulation level study. And this is again not my work. It's the work of my colleague Ashla Marathe. So the problem here is this is actually a real problem which got posed a few years back by one of the public health agencies. So when there's an infection going on, you have a limited supply. Do you distribute it through like a public health sector, through hospitals? Or do you sell it? Do you give it to the market and let them sell it? What is the best way of doing this allocation? So if you so this problem brings up all these issues of market. So the demand is going to depend on price. The prevalence will depend on the network structure and how people behave and so on. So there is both an individual behavior and organization level behavior. There are many different metrics one needs to consider. The infections, can you recover the cost of this medicine, what the issues of allocation and so on. So the study that Ashla did, she had models for individual behavior and these organizations, so the markets. So individuals do isolation if they feel there's a lot of prevalence of the epidemic, and their demand for this antiviral is going to be based on price. So they are sensitive to the price, and this is one function they used for the demand. This is from some prior literature on healthcare economics. And if the price goes up, the demand will go down depending on their risk aversion. I'm going through this really quickly because I'm running out of time. I'm happy to come back to this later if there are questions. There is some limited supply of antivirals in the study, and it's allocated between hospitals and markets. And the study was to figure out is there some split which is good. So the extreme case is give everything to the hospitals, give everything to the market, and so on. So the hospitals will give it, will administer it to whoever gets show symptoms and ends up at the hospital till they run out of supply. The market will choose a price and then give it on a first come first serve basis on that price. So if so here this is where demographics will come in. If somebody can't afford that from the market, cannot afford the antiviral at that price, they're not going to be getting it. So here is just a flavor of results from their work. So first thing is if you this is not surprising. If you allocate, so this is the fraction allocated to the hospitals, and this is the attack rate, and of course it goes down as more and more is allocated to the hospital. On the other hand, if you look at the revenue, versus the fraction allocated to the hospital. As you allocate more, the revenue goes down, and you cannot recover the cost. And so they find that there is some optimal split where you can recover the cost. And their conclusion from that study is basically there is some, so the split makes sense. Hospitals should be given some priority, and this the decision actually depends on a threshold. If it's above threshold, then distribute via the market, but if it's below some threshold, it's better to do it through a public. And individual behavior has a huge effect. So the household level isolation brings the peak infection down by a substantial factor, and the demand, prevalence based demand, also affects the peak by in the study 30 days. So let me maybe conclude this part. So we looked at network based formulations for interventions, and once you bring it in this form, the tools from dynamical systems, spectral graph theory, and approximation algorithms, which all come handy. There are lots of new challenges, so many of which we haven't even addressed here. So there are many multiple and competing objectives. There's lots of logistical issues. It's not just deciding whom to vaccinate, but how do you distribute them, and so on. And in reality, in the yearly flu season, there is production schedules which need to be also taken into account. The other thing, we've been working with a known network, but it's in reality it's not known. You have some models for it which you need to work with. There's all kinds of uncertainty of the source, the epidemic parameters, and so on. And so I talked about one way of one simple formulation for taking individual incentives into account, and that needs to be built much more. And then finally, there is coevolution of the disease with network, which really changes the whole landscape, and it's a really hard problem. So let me just a few minutes. So how much time do you have? 5 minutes? Okay. So let me quickly show you some tools that our group has developed for public health agencies. And so you can see in different kinds of interventions which are already there. The eventual goal is many of these optimization methods will also show up here. So let's just so you can set up. So this is a epidemic simulation tool which has been developed for several agencies, and let's just so I'll not start a new experiment given the time, but you can just Google for this and you'll see the so let me just open something which has been done, and you can see the kinds of so one can set up underlying this tool is not sure why this didn't. Oops. So underlying this tool is a population model. We have synthetic network models for many different regions in the US and across the world. And so in India, we have a model for Delhi, and a model for Bangalore is being developed. So one can set up simulations for different kinds of diseases. You can specify the disease model. So this is saying for this is some kind of flu model. This is the incubation period, the infectious period, and so on. We can set up. Oh, I don't know what happened. You can set up initial conditions and so on, and you can look at epidemic simulations on those networks. And then this, so you can specify them from the front end. These simulations are computationally really challenging problems. So there's a backend which does parallel simulations on some clusters that we have. So let me just show you some the kinds of analysis which comes out of it. So I'm just opening some old experiment. I'm trying to find one which is likely to have some interesting results. I'll just try one more page. If not, I'll just. As you can see, a lot of people have been using it and stores. Okay, so let's look at this one. Oops. So this was some analysis which was done for a model for Seattle. So it involved trying out some interventions and looking at like epi curves over those interventions. And so this kind of tool has been used by analysts for just what if scenario analysis. So if what happens if we vaccinate this kids, or we vaccinate some other subpopulation, or close schools and things like that. So this is not doing any optimization right now. It's there are all these interventions you can try out manually, all kinds, and see plots like this and decide. The eventual goal is we are going to put a wrapper around it which will optimize over some given space of interventions and also give you the best one. Okay, so let me stop here. If there are any questions, I can.
How did you reconstruct the Delhi social network, for example?
So it's a different talk. So it's a complicated process. So the first thing is there is no, you can never get a real contacts in a city. What you can get instead is all kinds of statistical samples. So you get census, you get land use, you can get activity surveys. So you can ask people to log the activities they do during a city and so on. And you can get a lot of demographic information and so on. So our premise is that the contacts in a city are basically the result of what people do, the activities people do. So we have a statistical methodology to combine all these different data sets and then come up with a network model which is like the best extent representation. So it's not like real, but it's like SimCity, but it captures and it can be calibrated to as many measurements that we find. So many of our the populations that have been developed, they are there on our web pages. Again, I should say this is not my work alone. I'm part of a large group, so there are many. So there's a statistician, an epidemiologist, a physicist, and many other people who have contributed to this. So several populations are already out there on our web pages, and you're welcome to try them out. And right. So that requires. So we are in the process of doing it. It requires getting the right kinds of data. So like one, some of it has to be bought, and some requires like getting surveys and things like that done. So we are doing that currently for Bangalore, and the plan is to try it for other cities as well.
Anil, since you mentioned that the isoparametric constant is related to the expander, I was just wondering whether we could relate it to the spectral gap of the Laplacian of the corresponding graph. So that would, relate to what Samit was speaking about, because Laplacian is related to the adjacency matrix. In principle, we could find some connection,
Right, yeah, right. No, absolutely, that is absolutely true. If the graph is regular, for instance, then you can say a lot more. But in general, these graphs are not, the degree distributions are really skewed, so there's not too much.
Okay. No, but am I right in
guessing
that
right,
it's related to the Laplacian spectral gap?
Absolutely, yeah, right. So the in the Laplacian, the first eigenvalue, so if you go from smallest to largest, the first eigenvalue is 0, and the second eigenvalue, the gap between the second eigenvalue and 0 is what determines this. In fact, there exist lower and upper bounds on lambda 2, which is related to the Cheeger inequality.
I want to start my question with an anecdote. So there was this architect, he was given the job of building the campus of a big university. And so when he was done with the job, when the university was finished, people noticed that he didn't construct any paths between the buildings. And so he said, let's open the university, let's start giving lectures, the students move in. And then he waited for, I think, an entire year. And then he looked at the grass on campus, and then he saw, where is the grass yellow? And here's where I'm going to put the paths, right?
Nice.
So can you envision a strategy of intervention based on this principle?
Right. So actually people have tried that. There are different kinds of mobility data sets. So there is this guy Brockman who's looked at the Where's-George network. Have you heard of this one? So like in the US, the US bill, $1 bill, you can register on the site called Where's-George. So if you put the serial number of that, so when you have that the $1 bill, it'll log that you had it at this location, and then let's say you sell it. I mean, you give it, and then it goes into the circulation, and somebody else does that. So basically, with that, you can keep track of where this dollar bill showed up, and you can get interesting mobility patterns from that. And so people have used mobility data of this kind to see what one can say about disease spread and about interventions. This was actually used in the 2009 flu, but the predictions which came out of this were way off, and there was a lot of controversy about how useful that is. So I think that's a really interesting idea. It's the problem is there's mismatch between all these different mobility, all these different data sets. The node sets are different, the time scales are different, and so combining them is a really non-trivial problem.
So, spectral radius minimization problem, for that you have used somewhere Perron-Frobenius theorem. Can I get some reference for that?
Sure, yeah. Actually, we didn't use anything other than the fact that the first eigenvector is positive.
Okay.
That's, we don't need anything more than that.
Okay.
The next speaker is Anil Vullikanti of Virginia Tech. Anil was supposed to also be here for the workshop. Unfortunately, he was not well and couldn't make it, but he mentions that towards the end of his talk, he would show brief glimpses of what he was planning to talk about in his workshop. Okay, and for the conference, he's speaking about economics of epidemic planning and response.
So thank you, Sitabra and Gautam, for inviting me. The program looks really excellent. I'm really sorry I couldn't make it earlier in the week. So this is joint work with a lot of people in our group at Virginia Tech and collaborators in other places, and this work has been funded by a number of programs. So this probably, this slide is not relevant here. Probably infectious diseases are a big concern. They've been a big concern worldwide for from the start of human civilization. Like the 1918 pandemic caused a huge number of infections. The good news is these days governments are like there's a lot more coordination, and we haven't seen mutations of the 1918 kind of lethality, like the SARS epidemic got controlled pretty easily, the Ebola one not so much. But the problem is the healthcare systems are usually optimized to work at the current infections. If there's anything worse, it's hard. The healthcare systems simply cannot cope up. There is inadequate supply of vaccines and antivirals, and lots of logistics issues. And there are new aspects which have come up in modern life, which weren't there as much in maybe 1918. So there's a lot more travel, immunocompromised populations, and urbanizations, and so on. And this influential article by Feinberg and Harvey from a few years back, it identifies these key issues in epidemic science in real time. And the thing I'll focus on is they list all these things which need to be done before or at the start of an epidemic. So figuring out what interventions would be required, the feasibility of these containment methods, stockpiling, and how to optimize, and so on. And then there is, once the infection starts, there is this work of trying to figure out what kinds of infection it is, calibration of those parameters, and figuring out whether it will be a big epidemic or not, and so on. So what I'll talk about today will be on this part, on the control part. And just to put this in perspective, this is like a real-time epidemiology life cycle. An epidemiologist usually, so in public health, so this is, when I talk of epidemiologists, this is more from public health perspective. So they have models of the population and the disease spread and calibration based on surveillance data, and then this is where public health people spend a lot of their time forecasting and figuring out what are good interventions and so on. So again, what I'm going to be talking about is more on this part. And here is an outline for the rest of the talk. I'll start with some mathematical models, and in particular I'll focus on network-based models. I'll define what I mean. And then I'll talk about 4 kinds of interventions. First I'll start with something which just takes the social objective into account. So designing interventions which optimize some social good, so like minimizing the outbreak size. Clearly that's that's really unrealistic because people don't necessarily comply. So we'll see how that can be modified to take compliance into account. And interventions like vaccinations, they cannot be done without taking individual utilities into account. People, you can make all the policies you want, people may follow them or not, and so that leads to some interesting game theoretical problems. And finally, I'll present this work by my colleague. This is not, the last part is not my work, it's by my colleague Ashla Marathe. She has, in some ways, it brings all of these issues into account, and it trades off individual and social objectives from a study that she did some time back on antiviral distribution. So these first three are more theoretical and based on network models, and the last one is using agent-based simulations. And please feel free to interrupt if something is not clear. I'm not sure what the background is. Okay, so this is a lay of the land on different kinds of mathematical models which are there in which are used in mathematical epidemiology. I was going to redo this slide. This is copied from somewhere else, but I forgot. So there are differential equation based methods which are the most popular, which have been studied for over 100 years. There are some limitations of those when you look at large heterogeneous populations, and so they've been extended using various kinds of compartmental patch based models. And then there is this other thread on network based models, which try to explicitly capture the heterogeneity in mixing. So there are again many kinds. So there's work on analyzing random graph models, and then there are activity template based, and then more realistic social network models that our group has been trying to develop. What I'm going to talk about will be more on this end of the spectrum. But let's just briefly start with how interventions are looked at in the compartmental models, and this is really oversimplification of what people do. So in the basic SIR model, individuals are in S, I, or R states, and you can, if you assume complete mixing, then you can describe the dynamics by these differential equations. I'm not going to go into those, but the epidemic can be characterized by the reproductive number. It's the ratio of the transmission rate and the recovery rate. And for our purpose, what matters is this nice result, which can be easily shown. If R naught is more than 1, then there's going to be a large epidemic. And this has a simple implication from the perspective of designing interventions. So everything depends on R naught. So if you modeling an epidemic involves basically figuring out what the R naught is. So if you want to control it, reduce R naught. And since R naught is this ratio of these two quantities, you can reduce R naught by either reducing transmission, so you can give vaccinations or use protective equipment and so on, or you can improve recovery. So one problem with this approach is it oversimplifies the mixing patterns. It doesn't capture heterogeneity in the population. People have dealt with these limitations by trying to add more compartments with mixing parameters between them, but then it loses its elegance and it becomes harder to analyze. So these models have been the workhorse of mathematical epidemiology for 100 years. They're easy to set up and so on. So some of the problems which have been found is like in the SARS epidemic, many epidemiologists estimated R naught in this range, and this was done through like the initial infections in crowded hospital wards, but it didn't really pan out. It didn't cause like a mega outbreak. There were many reasons for it. In the outside world, the infections were not spreading in like crowded wards. The other big thing was people changed their behavior. So it's not easy to reduce everything to R naught, and indeed people have pointed that out in recent years. So the point is there is some challenge in trying to design interventions which model the real world through just directly through compartmental models. I mean, people do that, and a lot more complexity goes into it. Instead, we'll focus on this approach of network-based models. So here, there is an explicit contact network of people. So these circles are people. There's an edge between them if they come in contact. So they're collocated and receive. There is disease can spread from one person to the other. So here is a cartoon of the one stochastic outcome. So initially this node 1 is infected, the red are infected, yellow are susceptible. So this node is going to be infected for one time period, and during that time period it tries to spread the infection independently to both its neighbors. After that time period it becomes recovered, so that's in green. This neighbor 2 did not get infected, but neighbor 3 got infected, so it became red, and the next time period this 3 got recovered, and the disease spread to 2 from 3 and so on. So the limiting state is when all the nodes are in S or R, and you can write. So this is one particular stochastic outcome. You can write down the explicit probability of this outcome happening, and you can write down the whole phase space. So so this approach, the dynamics depends on the network, and there is these problems become much harder to analyze. There is some work on understanding the effect of the network structure, which is known to be very significant. So there is a phase transition like in the differential equation based models. There is some kind of phase transition in some network models. So for the basic idea is there is a threshold for the transmission probability, such that if the probability is below this threshold, there are few infections. If it's above, there are lots of infections. This has been shown rigorously in a few models, so like in the complete graph and lattices and random regular graphs and some expander graphs under some conditions. It's not it's open whether this kind of thing holds in like arbitrary networks. And we've seen empirically, and other people have shown empirically, if you just vary the transmission probability, this number of infections does seem to go from suddenly from few to many. So probably there is a result waiting to be shown. So let's talk now about intervention problems. So that's the focus of my talk here. So what are we given? We're given a network. I say maybe because maybe you don't have the network explicitly, maybe you have a distribution and so on. So we'll come to those things towards the end. There is a initial set of infected individuals, you're known, or maybe you're given a distribution on that. You're given some resource constraints. There is some model for how the disease is spreading. So in this SIR model, the disease model would be the transmission probability, the recovery time, and so on. There are many objectives for these interventions. So the simplest would be whom to vaccinate so that the expected number of infections is minimized. But that's not the only one, or not necessarily the only interesting one. There are many others, like reducing the epidemic duration, reducing the peak, or delay the epidemic. And there is a lot of individual utility issues which come in. So this is a very generic way of